2.2, identifying functions from graphical patterns. So you're basically going to look at a function and you're going to say, I know that this function is linear, quadratic, exponential, or power. And then you're going to try and come up with the function for that using algebra. So that leads us to our essential question. Given the graph of a function, how do you know whether the function is exponential, power, quadratic, or linear? And find the particular equation algebraically. All right, you're going to need a couple of things for this lesson. One of them is the 2.2 handout that I gave you. So you need Exploration 2.2. That needs to be part of what you have here. And then you're also going to need your parent functions or your parent graphs. Okay, so hopefully you have those with you. That's going to reduce a lot of extra writing. Okay, so we need these two things. Before we get started, though, because most of this is stuff that you already know how to do, or maybe you forgot, but you've already learned. Let me introduce you to one concept that potentially you haven't learned about. So that is the concept of concavity. So concavity refers to a portion of a graph. So let's see. It's the actual curved portion of a graph between 2 points of inflection, which is probably also a new word for you, points of inflection, or asymptotes. Okay, so I'm going to draw a picture to help explain what the heck concavity is. So I'm going to draw it kind of big. It's going to take up this section here, and I'm going to end up labeling a whole bunch of stuff on it. So I'm going to do a curve. We'll just leave it like that. Okay, so first of all, there is a point of inflection where this thing changes direction. So you can see that here, it's kind of curves facing upward, and then it starts to curve facing downward. Okay, so that point of inflection is the point where it goes from facing upward, being curved upward, to being curved downward. So we'll estimate that the point of inflection is about here. So we call this point of inflection. And this is where the concavity changes. So I'll put where concavity changes. Okay, so we have two types of concavity here. We have concave up, which is on this side. And then we have concave down, which is over here on this side. Okay, so what do we mean by concave up or concave down? Well, basically, you can think of that hollowed out side. So this top portion here, the side that hollowed out side is facing. So for concave up, we'll say hollowed out side faces up. And so concave down, your hollowed out side faces down. Okay, now another way that I've always thought about concavity and how you can tell, so one way is to say, hey, which way is this hollowed out side facing? But I've also thought of it with tangent lines. So if you can draw a tangent line below the curve, then that means it's facing concave, it's concave up, okay? So for example, a tangent line, remember that's a line that's just going to touch the curve at one point. So if I can draw this tangent line, well, pretend like it touched it at one point. I can draw this tangent line below the curve, means that I have concave up. Okay, so I'm going to also write a little tangent line below curve. So that's kind of another way of thinking of concave up. And then if it's concave down, where would I want to draw the tangent line, right? I can't draw it below it, because if I try and draw a tangent line below, it's going to not be tangent. It's going to touch it in more than one point. So the only place that I can draw a tangent line on a concave down graph is going to be above. Pretend like that's hitting at one point. So this one, the tangent line is above. So you have a couple ways of thinking about concavity. Concave up, hollowed outside faces up, or the tangent line can be drawn below. Okay, or concave down, the hollowed outside faces down, or the tangent line is drawn above. Now notice that concavity has nothing to do with whether or not this graph is increasing or decreasing. Okay, so remember this point of inflection is where the graph changes from concave, in this case concave up to concave down. So I'm going to draw like a little divider there. And you can see that on both sides, whether it's concave up or concave down, we have the graph both, like here it's decreasing, but it's also decreasing over here, right? So concavity has nothing to do with the fact whether or not the graph is decreasing. And then we can also see on both sides, like here, it's increasing, but it's also increasing on the concave downside. So this is also increasing. So that's kind of concavity in a nutshell. You're going to need to be familiar with concave up and concave down. So that's more than the word concavity. You're going to need to identify whether graphs are concave up or concave down. And you have a couple of ways of thinking about that. Okay, so moving on from there, we're going to work on the exploration. So I'm going to kind of let this guide my lecture. So as we discuss, for example, an exponential, if we get an exponential problem, then we'll discuss exponential functions, and hopefully all of that information will be on your parent graphs. Okay, so moving on to exploration 2.2, graphical patterns in functions. So number one, we're going to identify what kind of function is graphed and find its particular equation. So number one, you should be saying to yourself, well, pretty easy. This is a linear equation. How do you find the particular equation? Well, you have many options. I'm going to refer back to our parent graphs paper. So when we originally talked about parent graphs, we learned about slope-intercept form, which you had known for a long time. We've got standard form, maybe better if you've got x and y intercepts or want to find x or y intercepts, and point slope form, maybe if you're given the slope and also a point, which is that x1, y1, that might be the form for you. Okay, and I want to just go over real quick that, this point slope form is really just the transformed form of a linear equation. So you can think of, the m being the same as a, minus h, well, that's the same as minus that x coordinate of the point that you're given, plus k, well, that would be if I took this y1 and I added it to both sides. So that's where that plus k comes from. So basically, it's just the transformed version of a linear equation is the point slope form. Here, we're not given anything but 2 points, so it's probably just best to go with slope-intercept form. So I'll start by finding my slope. Which ends up giving me a negative 12/5. I'll take that, plug it back in, and use a point to find my b. So why don't I use the second point? negative 96/5. So I'm going to have to add that 96/5 to both sides. Let's see, so this is going to have to be 13 times 5. That's going to give me 65/5 plus 96/5. So what is that? 161/5. Oh, and I'm off the page. I'm sorry about that. Which is approximate, oh no, it actually is. I'll keep with fractions. It actually is 32 1/5. So my equation for this is y equals, and I'll turn my slope into a mixed number, so negative 2 2/5 x plus 32 1/5. And I'm also going to circle the other part of this answer. Now, how can I double check to make sure that I have the correct answer? Well, that's what problem 2 asks you to do. Check your answer to problem 1 graphically. So actually use your grapher. Use your graphing calculator. And does your graph agree with the given one? And it does. I'm not going to waste your time by getting onto my graphing calculator to double check. You guys all know how to use your graphing calculator. When it does, then you just say, yeah, checks. Okay, great way on a test to know whether or not you've got the right equation. If you're allowed to use your calculator, great. Take that equation, plug it in. Okay, number 3, is the graph in problem 1 concave up, concave down, or neither? So it's a linear function. So does it ever, change directions? Does it have that point of inflection? It doesn't. Okay, this is just a linear function, so there's no concavity, there's no curvature at all to it. Okay, so we'll say neither. Okay, moving on to number 4. So what graphical evidence do you have that the function graphed is an exponential function, not a power function? Find its particular equation. Okay, so they're telling you that this is an exponential function. So in my parent graph, I'm going to look. I have exponential. So when we did this, and there's the transformed version. I'm not going to worry too much about the transformed version. We're going to focus on the y equals a times b to the x. So exponential was y equals a times b to the x. And then the power, so the power function, this was y equals a times x to the b. Okay, so those are our two functions that we need to compare. Let's see, while we're at this, let's go through exponential functions. Let's just review them real quick. So exponential functions, you're going to have an asymptote. Okay, so if we're just looking at like y equals a times b to the x, then your asymptote is the x-axis. Okay, if a is greater than 0, then this thing is shooting up when b is greater than 1. Okay, that means that you can think of like the penny predicament problem, right, that I asked you last year. Would you rather me give you a penny and double it every day for 30 days, or would you rather take, I think it was like $10,000? And if that penny that we were doubling, that would be our base, that would be our 2, right? And that ended up growing to like, I forget, I think it's like $1 billion. It ended up being a whole bunch of money. Okay, and we realized that, if b was something bigger than 1, this thing was going to grow exponentially. However, if b was something in between 0 and 1, it was actually going to shrink exponentially. Okay, so those were our exponential functions, and our asymptote was moving. If you had a transformation, our asymptote was going to move, and our asymptote would be wherever that shift, that vertical shift ended up, that y equals k. Okay, so for exponential functions, let's see. why is this not a power function and instead an exponential function? So let's just look at the y-axis. So let's compare the y-intercept here. Okay, so this thing is crossing the y-axis at some number. I'm not sure exactly what number it is. I'm sure I could figure it out by plugging 0 in once I get the equation, but we're not going to even worry about that. For an exponential function, if I want to figure out what the y-intercept is, I plug 0 in for x, and basically that turns this b to the x power into 1. So you end up with whatever a is. And I think we should have that. You should have that on your parent graph, right? Okay, so this would really go through whatever a is. That's if you don't have any shifts. Okay, so your y-intercept is usually what a is, as long as it hasn't been translated anywhere. Well, a power function is different than that. So if you were to put 0 in for x, because we're talking about being on the y-axis, you put 0 in for x, well, that turns x to the b power to 0, which turns this whole thing to 0. So in a power function, your y-intercept would be 0, 0. Well, our y-intercept right now, I'm not really sure what it is, our y-intercept right now is 0, a. Which that's why this thing right here is not a power function. So you could say a power function y-intercept is 0, 0. And exponential functions y-intercept is 0, a. So that's the graphical evidence that we have that we know that this thing's an exponential function. Okay, now from there, we're going to come up with the actual equation. So we have 2 points. We're going to use our exponential function, which is y equals a times b to the x. Now we have 2 points, so we can come up with 2 equations and use some substitution to actually come up with our final equation of this function. So our first one will be that I've got 4 equals a times b to the 3rd power. And our other equation is 9 equals a times b to the 8th power. Now hopefully it's ringing a bell. Oh yeah, I remember what I'm supposed to do. So we'll solve one of these for a. So if I do 4 divided by b cubed, I get a. I'll take that a value and I'll plug it in over here. So I get 9 equals 4 over b cubed times b to the 8th. And then I'll keep simplifying that. So I end up with, you should be able to see that you could put b to the 8th over b cubed. That would leave 4 so that I can divide it into 9. So 9/4 equals b to the 8th over b cubed, which really then gives me 9 to the 4th equals, simplifying here, we get b to the 5th. So b is going to equal, and I can take the 5th root of both sides, or I can raise both sides to the 1/5. So b is going to equal 9/4 raised to the 1/5. Now I can take that value for b, and I can plug it back in over here and get a value for a. So a is going to equal, and we can simplify all this and get it in our calculator in a minute, 4 divided by b cubed, which is really 9/4 to the 1/5 cubed. Okay, so b is really approximately 1.176, and a is really approximately 2.459. So my final equation becomes y equals 2.459 times 1.176 raised to the x power. So that's the final equation. And this is our first answer to why this ends up being an exponential function, not a power function. Now check your answer graphically. So again, you plug this into your graphing calculator. Again, I'm not going to waste your time. It'll take me forever to plug that in. So you can do that, or I would just highly recommend that you do that on your assignments and practice that for a test. Is the graph in this problem concave up, concave down, or neither? So again, a couple ways that we can think about this. Hollowed outside. Which way is it facing? Okay, the hollowed outside, which is this side, is facing up. Another way I can think about it is if I try and draw a tangent line, so a line that just hits this thing at one point. Okay, if I do it up here, I'm going to end up intersecting that graph more than once. I'm only allowed to touch it once. So I do it below. If I can draw the tangent line below, then this thing is concave up. So we know that this is a concave up graph. Okay, moving on to number 7. What graphical evidence do you have that this function is a power function, not an exponential function? Find its particular equation. So one thing that's important to understand about power functions is that sometimes they don't cross the y-axis. Sometimes there is no y-intercept. So going back to our parent graphs, let's talk a little bit about, and you might want to add some of this to your parent graphs. So a power function has this form. And if it was translated, it would look like this. Now, usually for most applications, it's not translated. Okay. Also, a lot of times, your domain is going to include basically all x values that are greater than 0 or greater than or equal to 0. Okay. So, if A is positive, these are basically the 3 forms that your graph can take with a power function. So this would be one form where A is greater than 0 and B is greater than 1. So that looks a lot like an exponential function. Okay, or you have this one where B is a fraction in between 0 and 1. A is greater than 0. Again, if A was negative, these are just getting reflected over the x-axis. Okay, so that's that graph, which looks a lot like a root graph, like a square root, right? Because B is going to be a fraction. B is your power, so now if B is a fraction, that means that you're taking some kind of a root, okay? And the last one is where B is less than 0, so B is now negative. So now you've got a negative exponent, which means, you're going to take the reciprocal of whatever the base was, okay? That ends up becoming something that looks like a decreasing exponential function. Okay, and that's when A is still greater than 0. All right, so your domain here, if B is some number greater than 0, okay, so if you're looking at these two here, usually your domain would include all reals, but for most applications, again, we're restricting it to where x is just greater than or equal to 0. Okay, what if B is a negative, okay? If B is something less than 0, similar to this graph here, it's really important that this graph excludes 0. Because if B is some number less than 0, so again, going back to this, B is a negative, that means that you're going to have to take the reciprocal of x, right? Which means you could end up dividing by 0. Okay, if x was 0, you would end up dividing by 0. Well, that's a problem. So anytime B is less than 0, what we do with a power function is we exclude x equaling 0 so that we avoid dividing by 0. Again, B would be negative. That would mean that we would need to do the reciprocal of x. Well, if x is 0, we got a problem. It's undefined. Okay? So that's this graph right here. And that's basically why. So we know that this is a power function because it doesn't have a y-intercept. Now we're going to find its particular equation. So very similar to finding exponential. And I think you got quite a bit of practice with this last year. So this is y equals a times x to the b power. Okay. And so now I'm going to come up with two equations and do some substitution. So first one's going to be 15 equals a times 3 to the b. And the other equation will be 2 equals a times 8 to the b. So I'm going to solve one of these for a. I'll go ahead and do this one. So 15 divided by 3 to the b equals a. I'm now going to take that value and plug it in here. So I get 2 equals 15 over 3 to the b times 8 to the b. And I'll go a little slower on this one. So this is 2 equals 15 times 8 to the b over 3 to the b. Now the reason I did that, one, I can now divide by 15, but also 8, I could rewrite this as 8 over 3 to the b power. So now I'm going to have 2 divided by 15 equals 8 over 3 to the b power. Okay, now how do I solve for b? How do I get b by itself? Well, the only way, and hopefully you remember your logarithms, but the only way that we can do this to get b by itself is to bring it down. Well, the only way we can bring it down is to use logarithms. So I'm going to log both sides. So this would really be log of 2/15 equals b times the log of 8/3. So now I can easily solve for b. b is basically going to equal the log of 2/15 divided by the log of 8/3. And when you plug that all into your calculator, you get approximately negative 2.054. So now I'm going to take that and I'm going to plug it back in up here to A to figure out what my A is. Okay, so I'm going to take this. Let's see, do I have room to draw somewhere? Yeah, let me just take this, plug it back in up here. So I get 15. Now, the more exact way to do this is to take this actual number and plug it in for B. But to save time in writing, I'm just going to go ahead and write down the negative 2.054. So 15 divided by 3 raised to the negative 2.054 is going to, well, it's an approximation now. So A is approximately 143.296. All right, so now our final equation is going to be y equals 143.296 times x raised to the b, negative 2.054. So there's our function. So once again, number 8 asks you to check it graphically. So you can do that with your grapher. And is the graph in problem 7 concave up, concave down, or neither? So again, you can ask yourself, which way is the hollow side facing? The hollowed out side is over here. Looks like it's facing up. But another way, another more probably accurate, like you'll always know the answer, is where can I draw a tangent line? Can I draw it above? Well, if I try and draw it above, it's going to hit that graph more than one time. Can I draw it below? Let's pretend like I did a good job and I only got it in one spot. Yes, I can do it below and I can end up getting a tangent line where it only hits it in one spot. So this tells me then that it's concave up. Okay, last one. Number 10. Identify what kind of function is graphed and find its particular equation. Well, hopefully you're reminded of this equation. This is one that we dealt with. Let's see. Where did I put it in my parent graphs? Ah, right here. We dealt with this, first thing in Algebra 2, and you dealt with it in Algebra 1 as well. So quadratic, where, you would end up with y equals x squared, that being this graph here. But maybe, it's been translated, so the vertex form that we used, or the transformed version that we used, has the A, the H, and the K, where your vertex was at HK. Or standard form that we used a lot to help factor. Okay, so again, if A is negative, this thing's going to be reflected over the x-axis, so it's going to be pointing down. So we know that this thing is quadratic. Now for this, I'm going to do a whole lot of work to come up with its particular equation. So you're probably going to want to go back to some paper, maybe use the back side. So this is going to be number 10. This is not going to be that fun. We were not given the vertex. We were given 3 points. Okay, so that means that we can use some substitution or some combinations. We're going to need 3 equations with 3 variables. Okay, so that's what we're going to get right now. And I'm going to use standard form because that seems like, again, if it was in vertex form, I'd just plug in the vertex and figure out what my A was, but I don't know that. So I have to do a lot of math right now. We all have to do a lot of math right now together, but this is our last problem, so it should be, that should be your reward. Okay, so we're going to use standard form. Now I'm given 3 points, so I'm going to come up with 3 different equations with those 3 points. Okay, so I'm given x's and y's. Hopefully you're seeing where I'm getting these, right? I'm just plugging in everywhere I see a y, I plug in the y value for the point. And then everywhere I see an x, I plug in the x value for that exact same point. So this is equation 1, equation 2. I got 3 variables, so I'm going to need 3 different equations, right? I need to figure out A, B, and C. So my third equation comes from that third point. Okay, so now what I'm going to do is I'm going to do a bit of simplifying. So let's see, we've got 26.6 equals 9a plus 3b plus c. 38.6 equals 64a plus 8b plus c. And 13.4 equals 196a plus 14b plus c. I think the easiest way to go about this is to use combinations to get rid of my c's. So I'll pair up equation 1 and 2, and then maybe equation 2 and 3, and make the c's opposite of each other, so that way they cancel out. So let's see, how about we take this first one and we'll make that negative. So I'll multiply this whole thing by a negative 1. So I end up with a negative 26.6 equals negative 9a minus a 3b minus c. We'll leave the second equation the way that it was. So this way the c's go away. And combining, we get 12 equals 55a plus 5b. Okay, so we'll keep that equation for a minute. And then we're going to do the same thing with the second and the third equations. We'll multiply the third equation by negative 1. So the second equation will keep, 38.6 equals 64a plus 8b plus c. this now becomes the opposite of what it was. So negative 13.4 equals negative 196a minus 14b minus c. Again, those c's cancel out, giving us 25.2 equals, that's negative 132a minus 6b. Now I'll take these two equations and I'll try and get something to cancel out if I combine them. Well, we got some pretty ugly numbers here, but I think I can work with the b's. So they're already opposites of each other, so now I just need to get them to be the same number. So if I could make them both into 30, this would be positive 30, this would be negative 30. So this whole equation needs to be multiplied by 6. This whole equation needs to be multiplied by 5. All right, so I'm going to end up here with 72 equals 330a plus 30b. That's after I distribute that 6. And then doing the same thing here, distributing that 5, I end up with 126 equals negative 660a minus 30b. Combining those two together, I get 198 equals negative 330a, and the b's cancel out. So now I can solve for a. So dividing by negative 330, a is going to be exactly, believe it or not, negative 0.6. And now I'm going to take that a, I'm going to plug it back into one of these equations and solve for b. So let's see, why don't we plug it into one of the two equations that I just made? How about this 25.2? Okay, so I'm going to take my a, I'm going to plug it back in up here. Okay, simplifying, that gives me 25.2. If I multiply these two together, I get a positive 79.2 minus 6b. And then from there, let's subtract the 79.2, so I get negative 6b equals negative 54. Well, that couldn't have worked out better for us. So b equals 9. Now I've got a and I've got b, and I can take them both and plug them into one of my original equations. I think I'm going to choose the one with the smallest output here, so 13.4. So we'll take 13.4 equals, let's see, 196 times a, which is negative 0.6, plus 14 times b, which was 9, plus c. So now my goal is to figure out what c is. So 13.4. Now 196 times 0.6, or negative 0.6, sorry, is going to be 117.6. Negative 117.6. And then 14 times 9 is going to be 126. And now solving for c, we'll take everything and put it on the other side. And when you do that, you get the fact that c equals 5. So now I've got all three variables that I was missing. And I'm going to now put that into standard form. So making sure I'm on the page here. We get y equals negative 0.6 x squared plus 9x plus 5. So where did I put my piece of paper? I'll go ahead and I'll write the final equation over here, but I'll definitely say that work is on other paper. And my final equation Now, you might go through and read through the examples in the book. When they're doing these problems, they're not doing systems of equations. They're actually doing matrices. Well, we didn't cover matrices last year. We'll get to that this year. But matrices is a way, actually a much quicker way of dealing with systems of equations. You can see that it just took us quite a while to deal with our systems of equations, all this work, and matrices would be helpful. But we haven't covered it yet, so we won't do it just yet. All right. Answering our last questions here. Check your answer. Okay, I've already checked it, so oops, that's down here, number 11. Check your answer. Remember, you would do it on your grapher or your calculator. Is the graph in problem 10 concave up, concave down, or neither? So is the hollowed outside facing up or down? It's facing down. Another way that you could do it is ask yourself, where can I draw a tangent line? On top or on the bottom? Well, I can draw a tangent line up here above it and only hit it one time. So let's see if I can do that pretty accurately, right? So I know then that this is concave down. Concave down. And then I'll let you answer number 13. What did you learn as a result of doing this? Hopefully you learned something that you didn't already know.